hier mal einen Speaker, die pro-Audio-Mensch ist und do-it-yourselfer and electromobilist. That's what you, yeah. And his talk is called
Sein
Sonic Alchemy. I think it's
Vortrag heißt Sonic Alchemy. Wir spielen mit Drehschaltern. Es geht um Sonic Alchemy, um Schallalchemie. Und ja, begrüßt ihn bitte sehr willkommen heißend.
Hallo, ich bin Veit.
Hello, I am Veit and I have the honorable function to talk one of the blockbuster talks, and I'm very happy that you're all here. Now, here is a disclaimer. I'm working for an Italian speaker company, and as always, when you're walking around and you know about these things and there are mistakes or accidents, then you can't just walk past it. So I'm interested in talking to you about what you can do better. There are so many interesting things with so many very simple tricks. You can do a lot of things better, but of course you can do a lot of things wrong as well. What we're talking about and looking at today is signal transmission and humming, sensitivity, something about the acoustic wave, and something about the comb filter. Then we're going to talk about watt and bass machines, time alignment, and the line of minimal variance, bass arrays and FFT analysis, and phase alignment. Well, of course, signal transmission you better do symmetrically. You can do it asymmetrically, but you can do both. Asymmetrically with this is the worse version, and the jacks or plugs we're talking here about is RCA or cinch. But classical jack, 6.3 millimeters and others. So you want to avoid some of these things. And there is an asymmetrical cable, a voltage or the wave, the frequency that you want to transmit. That's the whole secret. You can see this on a mobile phone. A couple of years ago, when you hear this, that's the mobile phone that's actually transmitting a disturbance into the microphone.
So how can we avoid this? Well, it's easy, just use symmetric cables and symmetric transmission over cables. The classic connector is the XLR connector, all the TTLR connector, that's for tip-ring sleeve. Das, was ihr vielleicht als Stereoklinke kennt. This is the stereo connector. It has nothing to do with stereo, it's just symmetric. It has one more pin. The trick is that we transmit our signal twice, once positive, once negative, so the waves are symmetric. If we connect this to a device, the polarity of one side will be switched. That has two advantages. There's a gain of 3 dB, and now if the mobile phone rings, the voltage will still be injected, but on the receiving end, the noise is once positive, once negative, and cancels out, and so we don't hear that anymore. So with low tech, we can really decrease the noise. This is typically the pin routing on the connector. This is how it looks like for the jack. The ring is really important, or just look at on your data sheet to make sure that the input is symmetrical. So now we know what cables to use, and we connect a lot of devices together. And sometimes there's a hum. You can't get rid of the hum, it seems like. So if you have a system with several audio devices, outlets, and we connect them all onto one power outlet, or maybe two power outlets that are at the same potential. This isn't a problem, but however, if there's a second potential somewhere, for example, if there's a party in a bar and the mixing desk is in one corner and the speaker is in the other corner, the outlets might be on a different potential, and the potential is goes over the signal connection, and you have the hum on the connection. What we can do is we can simply disconnect the shield, but you should not do that. That's ghetto. Just use a symmetrizing box, a DI box. It can symmetrize an asymmetric signal and has what we call a ground lift, and that will cut the potential. We can also use a galvanic isolator. This will also get rid of the potential difference, and the hum ideally should be gone. Okay, so this was the two biggest problems. Maybe we want to put up speakers for music or whatever. And then there's a question of how loud can this be? So what influences the loudness of speakers? What's important is the sensitivity of these speakers. Sensitivity is level of 1 watt at a distance of 1 meter, but at which frequency? The data sheet will typically give you 1 sensitivity. This is, as an example, is a high frequency speaker. We are just looking at this is another example for a mid-range speaker or a low-range speaker. Looking into this is a 18-inch woofer. It's relevant below 100 Hz, but we can see it's not very sensitive below that frequency. We have to live with this. It's one of the problems we have in the audio. These nonlinear issues can be handled with filters, but the fundamental issue just is there. So if we don't understand the sensitivity of the drivers, the catalog number doesn't tell us anything about the loudness. Sensitivity is always relevant.
So we now know that sensitivity is relevant, and we still care about the electrical sensitivity. How do we scale speakers if one isn't loud enough? Can we just put them together? You think you already know, it's all not that easy. The electrical current goes into the loudness logarithmically. That means that doubling the voltage doesn't double the loudness. So the other way around, if we have 1 kilowatt and we double that to 2 kilowatts, we only get 3 dB of loudness gain. Another problem is that we lose some loudness over a distance. Per distance doubling, we lose 6 dB. So with 2 meters, we have 124 dB left if we have 130 at 1 meter. And now we talk about dB, and the question is, how relevant is that? That is psychoacoustically to be looked at. For each double loudness to be perceived, we need 6 dB more as a human. So if we want the perceived loudness to be more linear, So if we want to have more loudness, then we would need to have a lot more electrical current and a lot more voltage. That won't work. To just double the things to double the loudness won't work.
All right. So now we know that we have to have more pressure and more speakers. Or is that the truth? No, it's not that easy, of course. The acoustic wave does play a role. It's a pressure change in the air, and the wave is going forward by molecule movement in a medium. So those waves, those molecules, they can add. It can happen positively and negatively. And another problem or another effect that's just there is that these acoustic waves can be reflected from, for example, walls. And what happens is that, so this is the phenomenon that comes out of this. Yeah. So here you can hear this. There are phase nonsense going on. So the phase nonsense comes from pop filters. And now we have a second loudspeaker. And this one does necessarily have a different distance to the listener. And what happens on the listener side is exactly that. The waves add. They meet, they add, and that's destructive. So now you can reckon why it's called that way. It's called comb filter because it looks like a comb. So now you have two loudspeakers, classically with the DJ in the horizontal, two speakers. If you just put it next to each other, you have a level fall of the level of the sound, the loudness. So how do we solve this problem? How do we solve this if we want to get it louder?
So this is a trend that has come about in the last 8 to 12 years to build asymmetric horns, put them on top of each other, or maybe horizontally adjacent, like a pizza, and they form a horn flare that emits just like the chassis. Or sometimes in very large venues, you have line arrays that are very tall and do only 15 degrees vertically. And the horn flare doesn't overlap, and so there is no comb filtering going on. That's not exact science. You can see that these speakers have some curving. They're angled to the bottom. This is a milkmaid calculation. So let's look at some simple speakers and not the professional stuff. Now we have again two problems or two approaches. So you can see the bubble here, which shows you that over the distance the speaker gets lower in volume. So the air sort of acts like a spring, and it attenuates the higher frequencies more than the lower frequencies. Okay, now if we have a professional what we can do is we can find the so-called line of minimal variance in that balloon, which is the longest line with the lowest variance. So we can draw in this line, and this is one where the acoustic impression is the same. In a more complex system, so with speakers that are scalable, we can use that. You can look at this as if it was one speaker. Here's a negative example. You'll see, close to the speaker, it's loud, and it sounds different than further from the speaker. Sometimes this is what you want. There's the dance floor, and then there's the bar. So why not? That makes sense if you know what you're doing. On the other hand, with very easy means you can place the 3 heads on one line, on the line of minimal variance, and have a very professional sound because the acoustic impression between all 3 speakers is similar or the same. Lots of problems in audio. We talked about reflections just now, specifically in the bass area. But subwoofers can have reflection problems with the wall, also with full-range speakers. And so sometimes, depending on the distance, the reflection that goes to the wall and back may just cancel out, and there will be no bass response at all. If there's an even number of wavelengths, it might cancel. It might work well, but not with a quarter wavelength distance. It's important to know the order of magnitude for the wavelength. So it could be about 10 meters, and then half of that, quarter of that. If you're asking yourself, where's my bass gone? It might help to just move the entire system by a meter or 2, and all of a sudden, the sun rises. It helps to switch on your ears. Oftentimes you have more than one speaker. The thing called stereo since the 70s been around. The reflection at the wall, that obviously exists as well for a left-right arrangement, just much worse. So what you can do here is this. So a speaker, like an 18-inch subwoofer, just by the way it's constructed, it has a characteristic that is directed. Actually, the directionality is almost not there. We talked about the comb filters just now. If we have a subwoofer to the left and a subwoofer to the right, stage is left and audience is right in these diagrams. So we don't need to discuss. That's the same on every picture, and you'll have this comb filter effect. And there's no attenuation to the back, which we actually would like to have. So the easy way to do this dramatically better is to put both speakers in the middle. No additional materials needed, the very homogeneous emission, very easy cabling, and we even have a level doubling. Okay, you're going to need some space in front of the DJ's mixing desk, and you still need the backwards attenuation.
And what we can do now is we can do carrier bass reflection. So we have subwoofers who deconstructively interfere to the back. It's called end-fired, so we have a second bass in front, which and the bass in front has a delay. So in the back, in the front they interfere constructively, and in the back they interfere deconstructively. And if we look at this for 55 Hertz, then we want to have 1.5 meters of distance. So grid to grid we have 1.5 meters that the bass in front has to be in front, and what we now get is this. So we don't have any attenuation drop, and we still have the homogeneous luminates, and we get our back attenuation. By the distance of putting them, we can set the center frequency where the deconstructive interference to the back works best. The drawback is we need 2 times the space in front of the stage that we would need normally. So, like for example, here in the first row we would have basses, which won't work for this room. But there is ways to do this. So we could do CSA stack. So we have a subwoofer array. It uses the same physical principle, but we put them on top of each other, and the one we had put in would have put in front, but we turn around that base by 180 degrees, and then we add the delay again, and then we have the addition to the front and the subtraction to the back, and we don't need as much space. This is good. We can do this in a lot of combinations. We can do this in horizontal or vertical ways. There's a lot of different ways to do this. And at the end of the day, we have, with a two-stack, we have some loss of amplitude, but we have a very homogeneous luminance. And we can have the backwards removal, and the wall won't make up any problems. So it's nice for well-working things like violence. We don't get the best material cost. So let's take a look at having it a bit bigger. If we have a lot of bases and we can just put them anywhere, well, then what we typically do is we have this like teeth, and we put them together, and
so we're looking for the distance not being too big, and we're going to look at it horizontally. We can see it better when we combine it. We have the gaps between the teeth, and we can see one, we can see another. So it's banding it together in different ways depending on the hertz count. And now you can see in the left and the right sides you wouldn't hear any of it, but then it would cancel itself out on the sides. So there are different solutions for this. It's called sub-air or curve for 45 degrees. You can you delay the subwoofers the more you get to the outside. So, for example, if we start in the middle for 0 milliseconds and we end up with a T4 at 6 milliseconds, so the pulse answer is close to the stack, but unfortunately, some qualities have to die, so it's always a discussion about the quality and the best ways. So this is what you see at the festivals, a combination of end-fired lines or curves or CSA stacks, and you can see it cancels out to the back well, and it opens up to the sides very nicely. And now here is a different version of a picture where you can see it easily. So here is no build-up delays, and this one is the 45 curve elliptically, which you can, it almost looks perfect. And now if we overdo it a little and fire with 70 degrees, the curve is still elliptic, then you can see that it goes well for a while, and then it kind of widens out in a way that we don't want to hear it. And then in the middle it gets really silent, it gets really less loud than the other parts, so it's not what you necessarily want. So the good and the bad, there is no line where there's only unicorns. At the end of the day, we always have to decide what you want to do. There is always things that you have to look at. There is homogeneous distribution, whether it cancels out to the back. There is the space that you need, and the way it spreads. So you can see this in the halls here when you have left and right hung speakers. You can look at it when you're looking and listening to the lectures. So you can scale. So there are top parts. We've looked at what we can do with subwoofers, and now we want to combine. Now we have to look at the goal curves curves that we're aiming for. So in studios or in the hi-fi area or also in classical areas, so we're trying to push it into the deep frequencies. So the major system is supposed to be as linear as possible. When you look at pop and EDM, and then in the other versions, you can see an over-heightened bass. So partially, we can put them in a way that the bass is only kind of covering the lower parts, and then we can overdo the bass, so to speak, by stacking them. So if you combine the top parts and the subwoofers on the lower parts, you can have these different curves as goals, and you can hit two flies with one hit, so to speak. So hey man, what's phase? Let's talk about phases. What's phase alignment? Phase is basically like percent calculations. So there is a delay. There is a continuously raising phase. The degree looks like this. We have this wave at 0 degrees, and then it goes through. And then you can keep in the back of your mind the phase circle. It's very interesting because I'm constantly talking about how bad it is with the comb filters, but actually if you look at it, you can see that the phase difference, when you combine two phases, it's rather neutral, or it can be destructive. With 150 degrees, we are at minus dB. And if you remember what we saw before, that's like half from the 3 decibel are half. So we're still talking about 5.5 dB constructive addition if we put it between 38 degrees and 90 degrees. So this is what happens, and that's what we kind of want to avoid. So nuances are important. And I'm talking about this because at the end of the day, this actually makes a difference. So what we want to do is we want to do a 2-channel measurement. Measuring means comparing. We have a measurement object and we have a reference. And we do this via a loop, a widespread, and we do it on the basis of a stimulus. Zenith sweep, white noise, other versions he names alternative. So one of them is an FFT-Analyzer. Was ist das? What is it? So about FFT, it's
I don't think I need to talk much about the FFT. The trick is that any signal can be decomposed into individual sine waves. So we can take the signal on top and then go to the bottom, and we have a part at 10 Hertz, some more parts at 20 Hertz, and so on and so on. This is our measurement setup. We have a computer, a sound card. Connected to the sound card is a Y-split, which is a cable that goes to the object under test, which should be the entire system, including the stage box, multi-core, mixing desk, cable, system controller, whatever. You can put all of this in. On the other hand, you put into the second input. The first channel carries the measurement microphone. I'm using a very cheap microphone by design here, because for a comparing measurement, it doesn't make any difference. That makes no sense to pay a lot of money, because you're using it for both channels. For phase alignment, it doesn't make any difference. This is not about the absolute frequency response. It's not about how it sounds. It's just the phase alignment. So use a cheap microphone. How do we do this? We use a stimulus, which often is pink noise. It could be something different too. Go into the laptop, do the FFT analysis and FFT magic, and out you get two diagrams. One is amplitude over frequency, and one is time over frequency. So we do the same thing with the reference. So one time we measure from the direct input to the Y-split, and then the entire system, including air, a microphone, and everything. And now we've done the measurement, and we have results. It might look like this. These are screenshots from a software that didn't measure. There's more softwares. I have a list. So you see the impulse response on top, and then the phase response in the middle, and the level response down below. From the impulse response, we know how much later the measurement comes compared to the reference. This will tell us if there's any reflections from the floor or from the wall, and you can do an order of magnitude calculation if there's anything in the way. Then you have the phase response or group delay, and at the bottom we have the level over frequency, and that tells us how the system has influenced the level. We've looked at the target curves earlier, so the way they look like, that's a matter of taste. It depends on the content. The phase alignment we want to do where the acoustical crossover happens. That is where the subwoofer and the high-frequency speaker overlap. The acoustic crossover depends on the level. So you can see how the acoustic crossover changes with the level. So you have to choose a music title of your choice and select which bass sensitivity, which bass application you want, and then you have the crossover. So you cannot have one system that works both for jazz and for something different, simply because the level of bass attenuation or amplification is different, but it is very important for the emotional response of a listener. So we do the phase alignment for the top part, get to the two diagrams, do the same for the subwoofer, get two diagrams, put the diagrams, superimpose the diagrams, so you can see the crossover where the blue and the yellow line cross, and you can see that at the top diagram this is not congruent. It doesn't overlap though, and we can do this by delaying our subwoofer, and then we have done the phase alignment, and if we switch all of this on, do the measurement again, in pink we can see, or in purple we can see that in the area of the acoustical crossover there's constructive interference, there's perfect impulse. So you can do, if you do too much of the delay thing, it could end badly. If you just give more and more delay in the system, 360 degrees later, it looks similar, but
But we can do that, solve that by turning both on, and we have that in the way across from where the bass is then bad. We can do these measurements with Rational Acoustic Smart, which is the classic thing most people use. There's also AFMG Systune, which is a bit older, but also works nicely and can do a lot of things better. There is Rita and RDNet Measure. That's where the screenshots are from. Disclaimer, that's my employer. There's also Room EQ Wizard. That's more. There's also Fritur, which is open source, but there is no face plot. But you could do that yourself. Meaning, at the end of the day, what do we want? We want our cables to be digital or symmetric if it has to be analog. We want to do this everywhere, whenever possible. We don't want the laptop to be with the aux cable. We have to think about the speaker position. If we don't do anything else, we could angle them a bit and put them on top. For the subwoofers, it's way more important, the positioning. And if you have time, think about phase alignment. Interpretation of these measurements, I showed you a very simplified version. You have to do this 5 or 6 times until you get a solution, but the most software helps you. And don't measure everything until it's dead. Some people can't really have it if you measure a lot with a lot of pink noise. So at the end, audio is always a compromise. If you don't want that, then you need to do lights. Then you don't have problems. But nobody was nice about the light show after the show. I hope I was able to show you a bit of my world. Thank you.
Thank you, Veit. Mike, thank you. Ja, danke schön für diese schöne Late Evening Show. Ich sehe ein paar Fragen. There's a mic there, number 2. The Internet.
Yes, the Internet has a question.
English speakers. Okay, so in German, I have a German question.
Ich habe ein Wohnmobil mit einer Brummschleife verursacht durch eine Kombination.
So I have a humming level with 2 adapters of 220 volts. The batteries were connected with mini jacks. The other cables were connected. It's not necessarily sure that it happened through because of the quantity or the mass. The humming could come from the range to the other side, the directiveness of to the other side, but it could also be a problem of, so to speak, atmosphere. So it really depends on the setup. So it's a very specific thing.
Challenge. Room. I have somebody. Yes, please.
I have one question. So, if there are feedbacks that can happen more often when you have a back-directedness and you don't have that under control, what would you recommend? Would you try to use this, or would you put the spreading to the back differently? So how would you do this? So that depends on the feedback. In the bass range, you can do this easily. In the higher notes, it doesn't bend as well. So there is a couple of effects. So there is some effect that you can get And if you take it from the top, then you already have this direction, but the filters don't... This might just be the worst way of doing it with a filter. So when you think about the filter that I'm talking about, this is like a sphere that takes signals from all the directions, but you can also have monitors where you can have a directedness of the sound, and then you can have with very easy means you can have less feedback. You can also do a delay on the microphone. You will avoid feedback with this, even if you don't have to filter as much. Okay, so we more have the problem that we're playing in a small cellar in the inner city, and the setup, well, makes the wall of the neighbors move. What would your recommendation be? Well, use a lot of concrete. Well, that is in the nature of the thing, you know. You could almost, think about it and invent it through the huge wavelengths. There is so much more energy in the bass sounds. And even though the walls are thick, you can't really do anything about it. You can try to do something with the back directedness, but it's idealized in my graphs. We of course have just looked at one in the back, but there is also speakers and options on the sides. Okay, so there is another question. Which software did you use for the visualization of your heat maps? Are there open source alternatives? My screenshots come from EastFocus. There is a classic from Mehr Sound, Map or Map Online. This has the best results, but you have to pay with your data. You have to register first. I do not know about an open source software that does the same job. But at the end of the day, you have to have speakers and visualizations of speakers that actually gives you a visualization of the data that they get, and that's hard to get. Okay, so I have an understanding question. Maybe I'm just not getting it. This backfire principle. When I imagine that there are 2 point sources for sound waves, and they're behind each other, and the phases add to each other, I would have expected a symmetrical picture. Why not? And that's because the one that is further away, you put a delay in. So the first wave goes on, and it arrives at the same time. The upper wave arrives at the same time as the lower one. And the one behind it. So they will cancel each other out, but it's not the same way that they take? Yes, exactly. Do you have some experiences with the open-air surround sound systems? And do you have some hints for this? I have heard about different installations, and I was always a bit surprised and maybe a bit disappointed about the phase deletion that was going on. Well, I don't know about that too much. The industry is driving the half train on immersive, but that's just a fancy word for quadraphonics or, this is nothing new, and it suffers from all those phenomena. And if you go through the phase and listen to the rooms, you can see and listen and hear that it really doesn't work as well. And I don't have a remedy for it all. But there is a wave-felt thesis.
Can you talk about wave field synthesis? Is this really a new era of sound? Well, sure, it's thousands of speakers, and more is better. It works well. If you have the money.
Thank you for these advices and so on. You can come over after some more there. Give a warm applause for Veit. Thank you.